All right, we are now recording. Let's get it set up from the current slide. And we need to do one more. This was example 4. We're going to do example 5. But before we get into example 5, let me go over a couple of announcements. Now, you've heard most of these before, so I'll try to make them quickly. These are not, okay, here we go. Graduation, application for graduation. A great thing to do, if you're graduating this term, you got to get that in, like right away, like immediately, okay, because we do have a graduation ceremony this term. We haven't done that in the past, in the fall. We are doing it now, so they've got to get these applications in time to get everything processed. Okay. If you're graduating in the spring, this is the best time to start the process. Do your audit first, your degree audit first, get your degree plan, see what you've taken, what you're currently taking, and what you still have to take. And then as soon as the spring schedule comes out, you can see how many of those things you can schedule, and if you can schedule them all, then do your application for graduation. And you do that online. So if you know of anyone graduating this term, let them know this, this term or spring term. If you're graduating later, just remember, start the application process the term before you're going to graduate. That gives you time to work out all the glitches and the kinks and everything else. Now, announced this one before, they're looking for note takers for this term. If you can do that and would like to, that would certainly be helping a student who needs it. And the Space Center is looking for peer tutors. I know this is happening on the Birmingham campus. I think it's probably going to be true here too. So check with the guy downstairs. I can't think of his name right now, but you could also go to Miss Leslie Harper on the Birmingham West campus and check with her there. Now, those are the school type announcements. Let me make one that I think I warned you early in the term, at the very beginning of the term, this would happen sometime or another. It's happening now, okay? Last week, they decided to have a requirement that we get something turned in for SACs that was due Monday of this week. They didn't give me, actually it was due Friday, but they didn't give me rights to do the thing. I tried to do it on Friday. They wouldn't, the system wouldn't let me. So I had to get rights on Monday morning and got them in this week. So that was that. They came out with this requirement. Jake's here. That we had to get. See, we have a SACS visit coming up. SACS is our accrediting agency, and that gets everybody panicked like crazy. And suddenly things that they should have been planning for all along, suddenly they realize they haven't done. So now we have a zero deadline to get it done. So I'm in the process of doing that. They decided they needed resumes from every instructor, not just full-time instructor, every part-time instructor, adjunct instructor as well. Well, and I've got to put those on the system. They can't put them on themselves. I have to do it. So they only gave me rights to put them on. So rather than having human resources do it, they have the resumes. No, we have to do it. So that was the second thing that was done for this week. They're due today. I don't know if I'll get them all in or not, but I'm going to try. And then spring and summer schedules are due this week. So they've had 3 really big things, 2 things for SACS and 1 thing for the regular. And I've been asking, when are we going to get working on summer schedules? Well, it's not open yet. They finally opened them Friday and said, get them done by tomorrow, yesterday, or something like that. So the bottom line to all that is the papers are piling up. I have had basically 0 time to grade papers this week. 0, okay? Not much hope of it today either. I only have 2 hours of office hours today. There might be a little bit of time this afternoon when my physical science class is doing a lab, but usually I can only get a few papers graded there because they all have questions all the time. So tomorrow I'll probably be working on spring and summer schedules. So the likelihood of getting much done then. We've got a wedding tomorrow afternoon, so I won't have any chance tomorrow afternoon to work on anything. And I'm almost praying for more rain this weekend, so I'll have some opportunity to get some stuff done at home. So I don't know. So if you haven't seen a grade show up yet, that's probably why. If I'm this far behind in grading, I'm even further behind on putting on Blackboard. So hang with me. This will all pass at some point. When, I don't know, but it'll all get over with. I'll get caught up, and we'll be back to normal. And we're getting close to having our second test. And let's see, how many first tests have I had in? Uno. Okay. So, and how many research papers have I had in? 0. Okay. So, need to have some more stuff coming in. Now, how did I wind up with? Yeah, that's right. Got it. All right. Let's move on. Example 5 in Chapter 4, Trigonometry, 4.6, graphs of other trigonometric functions, meaning other than sine and cosine. And we're on example 5, which is sketching the graph of a secant function. And it says, see larsonprecalculus.com for an interactive version of this type of example. So even though it's not on the PowerPoint, it is at larsonprecalculus.com. It says, sketch the graph of y is equal to secant 2x. Y is equal to secant 2x. Okay? How would you begin a problem like that? Absolutely. Graph its reciprocal function, which in this case is the cosine function. Okay? Now, but before I start graphing it, let me write it first. You want the secant function in blue or dark color. What color do you want your cosine? Purple. Okay. All right. So let's first do y is equal to cosine 2x. So let's start doing our parameters for cosine 2x. What are they? Help me. A is 1, so that implies the amplitude is 1. Okay? Next, B is 2, that implies the period is pi, 2 pi over 2, which is pi. Okay? Good. C is 0, so there is no phase shift. D is 0, there's no vertical shift. So we got what we need. What do we do now that we know the period is pi? Divide by 4, so period over 4 is pi fourths. There is no phase shift, so that will determine my interval. So I'm going to tick off, I'm going to go back to black, I think, or dark. It's not really black, but dark. And tick off some pi fourths. 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, 2, 3, 4, 5, 6, 7, 8. And then up and down. What am I doing? How did I do that? Okay. We'll do 1, 2, 3, 4, 5, 6. I don't need that many. And down 1, 2, 3. Okay. And we'll let that be 1, 2, 3, 4. This will be negative 1, negative 2, negative 3. Okay. So, our horizontally, our interval is pi fourths, pi halves, pi, and 2 pi. Okay, I didn't fill in all the blanks. Minus pi fourths, minus pi halves, minus pi, and minus 2 pi. Okay. So, help me plot the cosine function. Where does it begin? You told me to do, let me get back to purple. Starts where? Okay, it starts at 1. So I'll start here, go down to 0, down to minus 1, up to 0. See, that's why I did my intervals, so I can lay them out, okay? down to 0, down to -1, up to 0, and up to +1. Going backwards, it's down to -1, up to 0, up to +1, down to 0, down to -1, up to 0, up to +1, and down to 0. So here's my cosine function. Okay, there's the cosine function. I did something wrong there. And I can't figure out what it was. No, it's right. It's right. Okay, I just got more tick marks on this side. No, it is wrong. There's something wrong here. 1, 2, 3, 4. -1, 0. Ah, I see what I did wrong. Okay. Y'all didn't see what my puzzle was? I was wound up at a, goodness, my whole thing disappeared, didn't it? Okay. Well, I need my black first. Sorry. I need my horizontal axis here. I lost it all. Okay. Now, we'll do the purple. There's a 0, there's a -1, 0, +1, 0, -1, 0, +1. See, at -2 pi, you should start at the same place. That's the whole number of pi's. Now, here's my graph. There. Okay. I knew you couldn't have this one ending here. What I had done, I had skipped my I-4 center. I'd done something really stupid. But you see, at the period, you better be back at the same location. And I wasn't. So I knew there was something wrong there. That wasn't what the problem asked for. It didn't ask for you to graph the cosine 2x. It wanted secant 2x. Why did I do cosine 2x? Yeah, because it's easier, and that's it. You nailed me here. Okay? What do I do with that now that I've got the cosine? Absolutely. Everywhere that the cosine is 0 because the secant is 1 over cosine, can't happen. So every one of these, you have a vertical asymptote wherever cosine is 0. Okay. And over, get out of there. Okay. Everywhere that cosine crosses the x-axis, you have a vertical asymptote. So draw them in. Okay? Now, what else can you do from here? Secant? How do you do that?
If it's a max, you go, it's like a up.
Okay. Yeah, you go in the opposite direction. Oh, I'm supposed to not be purple anymore. I'm supposed to be my dark color. Okay. So here you'll be going up. Here you're going down. Here you're going up and up, down and down, up and up. Be sure you have these rounded, the cosine and the secant, because they are rounded functions. Why is that not writing? There we go. And down like this. And up like that. And so on. Okay? That's your cosine. I mean your secant. This one here. The purple cosine, just to help you give you a basis to draw, this is the function you're looking for. Okay. Some things to note about it. Secant is never its range never goes in or out of your amplitude. It's all, inside your amplitude, plus or minus the amplitude. Always outside, okay? Amplitude for cosine. Secant doesn't have an amplitude because it goes to infinity in both directions. But it starts at the maximum of the cosine and goes up, and starts at the minimum of cosine and goes down. And it's not quite a mirror image, but it's the same kind of a picture going down. Does that make sense? Like you said, this is the easy way to do secant and cosecant. In fact, it's about the only way unless you just do a graphing thing. All right. And you'll see their picture in the book is almost as pretty as mine, not quite, but close. Okay. There is a checkpoint there. Please try to do the checkpoint as soon as you can after class is best. All right. Any questions on graphing tangents or cotangents, secants or cosecants? Okay. If not, all four of those have places that are not defined. Those are going to be vertical asymptotes. Usually your best place to start with graphing is put those vertical asymptotes in place, and then with secant and cosecant, graph the sine and cosine first. They let you know where the vertical asymptotes are. For the tangent and cotangent, figure out where the vertical asymptotes, put them in place, and then draw your tangent and cotangent in between. All right. We're now moving to damped trigonometric functions. And be sure you put your P in there, okay? And we'll go from there. You can graph the product of two functions using properties of the individual functions. Now, we haven't done much of that, so this is the first case, I think, that we've done something like that. Here's an example. If you're plotting f of x is equal to x times the sine of x. Two functions, you're plotting their product. As the product of the two functions, y is equal to x, and y is equal to sine x. Two different functions, and we'll plot them and see what the product comes up being. Now, we'll use the properties of the absolute value and the fact that the sine x is always less than or equal to 1. Absolute value of sine x is less than or equal to 1. Okay? Now, if you take this, and of course the absolute value is always going to be greater than or equal to 0, so you can put the less than or equal to 0 out here. But then if we take this and multiply this by absolute value of x, that by absolute value of x, and this by absolute value of x, then you get this. 0 is less than or equal to x sine x, absolute value, and that's less than or equal to absolute value of x. Okay? Well, what did that do for us? It almost gave us what we're looking for. We have it on the positive side. We'll have to fiddle with the negative side in a bit. Okay? So, what we do with that then, to get rid of the absolute value bars, then you do a minus x over here, less than or equal to x less, and that's less than or equal to, and it really still should be minus absolute value of x, because x could be negative. So that's why you don't want just minus x there, you have it backwards. But minus absolute value of x, less than or equal to x sine x, less than or equal to absolute value of x. And that's what they did next. Okay? Made sure it was negative here, that's less. Okay. Now we've got that the x sine x is always in between the absolute value of x and the absolute minus the absolute value of x. So that gives what I call the envelope. Okay? I also call it something else. I'll get to that in just a minute. Okay? Which means that the graph of f of x equal x sine x lies between the lines y is equal to minus x and y is equal to minus x and y is equal to positive x. Okay? Furthermore, because the sine f of x equal x sine x is equal to plus or minus x at your half pies, where sine is equal to 1 or minus 1. Okay? At every half pi, sign is either plus 1 or minus 1. So they are actually going to be on that line at those values, and they're going to be at zeros anywhere you're at n pi, your whole pi, because sign is 0 at n pi. Well, whatever x is, 5 million, sign is going to be 0, so that would be that. So where n is an integer, the graph of the f touches the lines plus or minus x, where x is your half pi, one of your half pi's. X-intercepts at n equal pi, x equal n pi, sorry. Now, that's one way to look at it. I don't know if this is helping you or not, but the other way to look at it is that, this is my little thing, I don't recall ever seeing this. I think of this as a variable amplitude. Because usually it's a sine x, right? So variable amplitude where x can be 0 at 0, 1 at 1, 2 at 2, you know. So basically that's going to be your amplitude. So when you reach your max or min, you're going to touch that variable amplitude, which is going up, you know, or down, depending on which way you're going. So to me, that's another way to look at it. This way sort of helps you graph it first, kind of. But the other way, to me, makes more sense because we already talked about amplitude. Now it's just a variable amplitude. Okay? So how does this go? And here's the one place that you do have a little bit of an issue with the way I did it, maybe. Sketch of f shown below, then the function f of x equals x sine x. The factor, the x factor is called the damping factor. Okay? Now, because that dampens or expands. To me, I just call it the variable amplitude. Okay? Now, here's the only little bit of a problem here. Okay? Your f of x is the product. Okay? Sine is an odd function. This is an odd function. So when x is positive, at least in the first quadrant, sine is positive, and x, of course, is positive, right? So positive times positive is positive in the first quadrant up until pi halves. Okay? Now, however, when x is negative, this is negative, of course, and sine is negative in the first quadrant that way, well, negative times negative is positive. So now you have an even function here, not an odd function. So you can't do the sine function as you normally would. You have to do the negative sine function here and the positive sine function there, because your variable amplitude is now negative over here, positive over there. So that's the only thing you have to watch out for with one like this. Draw your, and I think consider these my envelopes. Everything's going to stay within that. Okay? So it goes up and down, at the same places it would have. Maximum at pi halves, an intercept at pi, minimum at 3 halves pi, intercept at 2 pi. Just the same as it would, except it's doing the variable amplitude. Same thing this way, except it throws it in reverse because negative times negative is positive. So now that makes an even function. This is the graph of the damped trigonometric function. This is just construction lines to keep you where you need to be. Does that make sense? All right. Now they're going to do a completely different damping factor. This time it's not x, it's e to the minus x. Okay? Now that means you have to think back and figure out where what that function is going to be doing for you. Okay? Now, you know, remember I said it's an envelope. Okay? The sign is always going to stay between plus or minus 1. That e to the minus x, though, is always what? Is that ever minus 1, say? E to the minus x? Use Jalen. Is e to the minus x ever minus 1, say? Something about exponential functions, they're always positive. Okay? So on this one, you have to figure out, and let's first map that. I call it the envelope, they call it the damping function. Okay? Does anyone know where, say, when x equals 0, what's e to the x? E to the minus x. E to the 0 is? 1, yes, okay. That's going to be 1. Okay? Now, okay, let's do a timeout here for a moment. I guess I should have started looking at the sine function, because that's going to determine my placement of my x values. Okay? Okay. Number 1, that's your variable amplitude. So we're not going to mess with amplitude now because it's going to vary. Your b here is what? Okay, your period is 2 pi divided by 3. The b is 3. Okay, so the period is 2 pi divided by 3. In other words, 2/3 pi. Okay? There is no phase shift or anything else. Thank goodness. That would be a real pain in the neck to try to do. So we'll do 1, 2, 3, 4, 5, 6, 7. Negative 1, 2, 3, 4, 5, 6. Okay? Now this will be 2 pi thirds, or 2/3 pi. This will be 4/3 pi. Oh, yeah, I'm sorry. I forgot to divide by 4. Sorry about that. Getting carried away here. All right. Let's divide by 4. The period divided by 4 is then what? 2 pi over 12, which would be pi over 6. Perfect. Okay, so this will be pi 6. This will be pi thirds. This will be pi halves. This will be 1, 2, 3 pi. Okay, minus pi 6, minus pi thirds, minus pi, and minus 2 pi. Okay, now, we'll get back to that in a minute. Your variable amplitude is going to be e to the minus x. We got the first point. When x equals 0, e of 0 is 1. Okay. Now, maybe not a bad idea to pull out the good old calculators and put e to the minus pi 6 and see what that gives you. E to the minus pi 6. So it's minus the x value, pi 6. What would that be? E to the minus pi 6. .59, so just a little bit over a half. How about e to the minus pi thirds? .35, so a little bit more than 1/3. Okay. E to the minus pi halves. .21, a little bit more than 1/5. Okay, you get the general idea. The next one's going to be pretty small, and then pretty small, and then pretty smaller, smaller, smaller. Okay? How about e to the minus of minus pi 6 would be e to the pi 6. 1 point what? 6/8, a little bit more than 1.5. Okay, get out of there. Okay, e to the 1/3. Pi thirds. Bet it's going to be off scale.
2.85.
Oh no. Okay, 2.85. Okay. E to the pi. 23? Wow.
You said
Huh?
pi, right?
Yeah, e to the pi. Go back and do e to the pi thirds again.
E to the pi thirds is 2.84.
Wow, that really comes down rapidly. Okay, so this is approximately our e to the minus x curve. Now, because the sign goes back and forth plus and minus, you have to mirror this across the x-axis. Okay, so e to the pi thirds was plus almost 3. This will be minus almost 3. That was plus whatever that was here and here. And then here was a little bit there, there, and there, 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 there. Okay. And this takes off and flies down here. Okay, draw your envelopes. Everything has to stay inside the envelope. Okay? Now, let's fiddle with the sign then. Sign starts at 0 and goes up to your maximum there, but your maximum there is now the envelope. Okay, that's as high as you can go. Back down to 0, a min down here, back up to 0 here, and a max right there, and a min right there, and a 0 there. So basically, you can see what it's doing there. On this side, it goes down to a minimum there, up to a 0 there, and then somewhere up there it reaches a maximum, back to a 0 here, a minimum somewhere way down there, and then back to a maximum, intercept here. So this function is basically doing this number. I shouldn't have it connecting there. Okay. It wiggles and jiggles from then on. Okay. So it goes extraordinarily high there, low here, up high. It doesn't meet up there. Okay. Comes down, finally intersects here, there, and now it's tapped out like crazy here. Okay. So that's the general concept. Graph your envelope function. Okay. Now this one, e to the minus x is never negative, so the sign goes by its normal SIGN sign, up and down, up and down. The previous one, because x was negative on this side, positive on this side, that made the sign symmetric about this was not. Okay. All right, does that make sense? Not at all? Okay. What are you missing? Okay. Tell me something.
I'm just trying to figure out how you're going with e to negative x.
Okay. Where it came from?
Yes.
It's right there. E to the minus x.
Say like what does that mean?
Okay, the exponential function, which is it's actually just a number, e, it's a base. It's 2.7, blah, 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 blah. It's an irrational number. It's kind of like pi, but it's not pi. It's 2.7 something or other. Irrational number raised to some power. Now, your calculators all have that key on it, e to something. You don't have to worry about what that irrational number is. Hit that key in it, you got it. So, that gives you the envelope. And here's some things about the exponential function. The normal exponential function, e to the x, never reaches 0, but gets awfully close to it for very low numbers. But always goes through 0, 1, and then takes off and goes. Every exponential function does that. E to the minus x just reverses and starts really high and comes down to 0 and then never reaches 0, but approaches 0. So that gave us this curve here. Okay. Now, we didn't start with that curve. I started to, but then thought better of it. We need to get our points for our sine 3x, so that's why we did what we did there. The period is 2 pi over 3. Divide that before you get pi 6. So you tick off these. That's going to be a 0, max, min, max 0, min, 0, max, 0, min, 0, as you take those off. And same thing going here, 0, min, 0, max, here, 0, min, somewhere down here, and then max. Because that envelope function, the e to the minus x, that's your, what I call a variable amplitude function. It changes, and if e is extremely large, then your maximum comes up way up there. When it's extremely small, then the maximum stays between those two. So that's your variable amplitude is how I like to look at it. Look, doesn't use that terminology as I do. Okay? And the function stays in between this. But because sine goes from +1 to -1, e to the minus x is always positive. You have to draw minus e to the minus x just to get the lower one down here. Okay, so you draw this envelope here, and your sine function then has to stay in between that. But it meets all of its max, mins, and zeros right in the same place as normal. Okay? Is that better? Okay. Now, let's see how they did it. You know, I have a sneaking suspicion that picture may be a little bit better, but not much, just a little bit better than mine. But let's see what it looks like. Okay? Now, they do a lot more talking here, or some different talking anyway. Consider f of x as a product of e to the minus x and sine 3x, each of which has a set of all real numbers as the domain. So no problem there on the domain. It's just the ranges are going to be a bit different here. Okay? Now, they go through this other way, and if this makes it easier for you to see, go for it. For any real number x, you know that e to the minus x is always positive, because e is never negative. By the way, e is the inverse function of the natural log. Natural log, you can't ever put a negative number in the natural log, or even 0 in the natural log, because it starts down here and goes up like that, and the inverse function of that would start here and go like that. So it's, whereas the domain of the natural log is always positive, the range of the exponential function is always positive. And the range of the log is infinite, which is all real numbers, but so the domain of e to the x and e to the minus x is always all real numbers. Okay. Domain is all real numbers. Okay. So we got that. You know that e to the minus x is always positive, and the absolute value of sine 3x is less than 1, between 0 and 1. And I have trouble figuring out, why don't they just say sine 3x is between -1 and 1. They put absolute value in here and then later take it off, okay? And I don't see why. Why don't they just say -1 is less than sine 3x is less than 1. It says the same thing, but they later are going to take that off. So why not take it off now? See right here, they take it off. So if that's the case, and then you multiply, if -1 is less than or equal to sine 3x is less than or equal to, then just multiply each side of those three sides by e to the minus x, and this will be minus e to the minus x less than this is less than that. And this is what we're looking for. So you plot your minus e to the minus x here, positive e to the minus x there, and you keep this thing always in between those two. So that's what the envelope is. This is the bottom envelope, that's the top envelope. And this has to stay between those. It reaches its max touching those, and the max touching this one, the min touching this one, the 0 is where they normally are. Okay. All right. Because alpha of x is that, is always plus or minus that at your half periods, okay? Your period was, boy, they say this so strangely. The period was 2/3 pi. Half a period is pi thirds. So starting at pi 6, the first max, and then half a period from there on, your plus or minus. That's where your maxes and mins are. Okay. So to me, this gets really. I read what it says and then have to rationalize it. Yeah, that's right. That's not helpful to me to see what it is. Okay, so if you do it the other way, it seems like it makes more sense. But that may be just me, my thinking. You have your zeros where you always have your zeros at your half periods. Okay, because zero here, a half a period later, zero again, and then a full period is zero. So every half period, every normal pi, now it's pi thirds, you have your zeros. Now those are good to plot, always good to plot, okay? And then the graph touches the curves at the maxes and mins and crosses the x-axis at the intercepts, same as before, okay? So this is how it looks, and you see it's almost the same way I drew it, okay? I did pi 6 so I could identify max, 0, min, 0, max, 0, min. After a while, you're so close you can't see anything. Min, 0, max, 0, min somewhere way down there, 0, max somewhere way, way up there where it intercepts that. So sure enough, this is what it does. Max and min on the envelope, because that's a variable amplitude, so that's how far it goes, and then your zeros are exactly where they would have been every half period. Does that make sense? Okay. So really the toughest thing is drawing the envelope function. Now, since the trig function is going to determine the period, and your zeros and the maxes and mins, I plot those first, and then use those values I know to plot, and that's what I had you do, e to the minus pi 6, e to the minus pi 30. That tells you where the envelope function is going to be there. And because it's an irrational number anyway, you can pick any number you want to. They're going to be weird numbers. So why not pick the same numbers you need here? This one, that one, this one, that one, this one, that one. And plot those, and then keep the trig function inside that envelope of your variable amplitude. Make sense? Kinda? A little bit? Okay. Now, that was example 6. Okay, and you've got it in the book. Now they're going to review, sort of summarize these 6 basic trig functions. This is from, the first 2 are from the previous section. Y is equal to sine x or cosine x. Domain, all real numbers. Okay? You have no places these are not defined. These are the only 2 trigonometric functions that's true. Okay? Range of sine x plus or minus 1. If you had an amplitude there, plus or minus the amplitude. Okay? That would be the range. Okay? Same with cosine. Sine starts at 0, cosine starts at 1. They're exactly the same otherwise. Take the sine function, shift it pi halves this way, and you got the cosine function. Take the cosine function, shift it pi halves that way, you got the sine function. Okay? Period 2 pi. Unless, of course, there's a b there other than 1, and then that changes. Okay? There's your basic sine and cosine. You need those for secant and cosecant. You come see them again. Okay? The tangent function and cotangent function, domain, the tangent never can be a half pi because it's cosine, sine over cosine. Cosine is 0 at every half pi. Okay? And sine is 0 at the whole pi. So that gives you your intercepts. Okay? But cosine 0, that gives you your asymptotes. Okay? If this had an a in front, that gives you the value at the quarter pies, what would be. If that a was 1/2, it would be down here. If a was 2, it would be up here. If it was 7, it would be up here. So that's where the a comes into play there. That's the value of the quarter pies. Plus at the left hand minus at the left hand, plus at the right hand. Okay. Cotangent function, your intercepts and asymptotes are reversed because it's cosine over sine. Everywhere the sine is 0, vertical asymptote. Okay. The whole pies. Okay? And your intercepts are then where cosine equals 0, those are your half pies. Okay? So don't do a line there. Point. Okay? Now, here's what I always remind myself when I'm drawing the cosine. The first quadrant is always positive. So if you have the vertical asymptote here, it has to be positive, and the 0 there has to come down like this, and then the pattern repeats itself every period. Period is pi for tangent and cotangent, the only two trig functions where the period is pi. Range, all real numbers. Only two trig functions whose range is all real numbers. Okay. All right. Any questions on those? And again, when you're graphing these two, because of the definition, I like to go and put my vertical asymptotes first. Tangent is sine over cosine. Everywhere cosine is 0, vertical asymptote. Okay? Cotangent is cosine over sine. Everywhere that the sine is 0, vertical asymptote. So get those in place. Then exactly in between every two vertical asymptotes is your 0. You don't even have to think about sine of 0 or cosine of 0. Just put them in the middle. And then on either side of that 0, halfway between your zeros and your vertical asymptote, your plus A and minus A. So that gives you your 3 points and your asymptotes. Draw them in. Really easy. Same thing we do with cosine. Get those asymptotes in place, these zeros halfway between the asymptotes, and then minus A's and plus A's, and plus A's and minus A's on either side. That's quarter pies, quarter periods. Done? Okay. Then your secant and cosecant. They left off the most important part. First, draw your sine and cosine. And then, based on that, vertical asymptote, where your this would be the sine would be 0, and max and mins were the at your full pies. Just exactly reverse for secant, because your max and mins are at your full pies. Your zeros at your half pies, so your zeros will be your vertical asymptotes, and your full pies are going to be your max and min. Just wherever the max would be for your cosine, that would be min for your secant. Wherever your min is for the cosine, that would be the max for the secant. Domain, all real numbers except for the reciprocal function is 0. So, for cosecant, except for full pies, and secant, except for the half pies. Okay? Range, always from 1 up and negative 1 down. 1 up and negative 1 down. Or, if you had an amplitude for that cosecant, then that would be your amplitude, a negative amplitude down, positive amplitude up. That would be your range. And the period is 2 pi because of the reciprocal of sine and cosine. The period is also 2 pi. And you see, to get a full period here, you would have to go from here to there. And that's a 2 pi range. Or from here to there. 2 pi range. Any questions? I think that's the last slide. Let's do the vocabulary. The tangent, cotangent, and cosecant functions are blank, so the graphs of these functions have symmetry with respect to the, first blank, choice of 2 words, even or odd, and these are odd. You're absolutely right. So the graphs of the 2 functions have symmetry with respect to the
Y-axis.
no, those are the even.
X-axis.
No. Origin. Okay. Let's go back. Okay. Notice it said cosecant, which is this one. You go to the right, you find the value up here. Go to the left, it's down there. With respect to the origin. secant function is the only one of these four that's even, and that's with respect to the y-axis. Whatever you see going on the left, you see the same thing going on to the right. Here, whatever you see going on the left, the opposite is going on to the right, or vice versa. So those are odd functions, so the graphs are symmetry with respect to the origin. Number 2, the graphs of tangent, cotangent, secant, and cosecant functions have blank asymptotes. Vertical asymptotes, excellent. Pretty exciting stuff, huh? To sketch the graph of a secant or cosecant function, first make a sketch of its blank function. Reciprocal function, perfect, okay? For the function f of x equals g of x times sine of x, g of x is called the blank factor. Remember? The damping factor, okay? Number 5, the period of y is equal to tan x is, period of, is what? Pi, exactly. Number 6, the domain for y is equal to cotangent x is a set of all real numbers such that cotangent x. Okay. Certainly that one's true, but x can't be in pi, where n could be 0 or 1 or 7 or 15 or minus 3 or whatever. Can't be in pi, because that would be where the sign would be 0. Okay. Number 7, the range of y is equal to secant x is range of y is equal to secant x. Okay. Okay, did you say 1 to infinity, negative 1 to negative? Perfect, exactly. Okay. And the period of y is equal to cosecant x is 2 pi, same as its reciprocal sign. Okay, homework exercises. I would definitely do all of 9 through 14. You'll only find the answers for 9 through 13 in the back of the book and at calcchat.com, but it was good to do them all because those are pretty easy to do, matching up. Okay? Then do any of the odds 15 to 37. They're all at calcchat.com, 19's at calcview. Do any of the odds 39 to 47. They're all at calcchat. Do any of the odds 49 to 55. They're all at calcchat. 51's at calcview. Do any of the odds 57 to 63. They're all at calcchat. 57's at calcview. Do either, and again, I think I would do all 4 of those, but you only find the answers to 65 and 67 at calcchat and in the back of the book. Then I would do either 61 or 69 or 71 or both. It's a conjecture type thing, which sometimes could be a little squirrely, but see what you can do with those. Then do either 73 or 75 or both. They're both at calcchat. And by the way, 69 and 71 should be at calcchat as well. Do any of the odds 77 to 81. They should be all at calcchat. And in the back of the book, of course. Then do any of the odds 83, either 83 or 85 or both. They should both be at calcchat. Okay, then do 87 is a true-false. It should be at calcchat as well. 89 is a think about it. I don't know if that's at calcchat or not. Graphical reasoning 91 should be at calcchat, and another one 93 should be at calcchat as well. All right, that finishes 4-6. trying to get this over with, am I? Okay. Okay. Is it getting to the witching hour? Oh my goodness. We've still got 5 minutes at least, don't we? Good deal. Thank you.
Yes, sir.
All right. All right, yeah. It's only 11:08. We go 11:15. Okay? So let's get started if we can. We won't get too far, but in 4.7. Okay? And these are dealing with inverse trigonometric functions. It's a little bizarre in some ways how I'm teaching 112 and 113, and back when we were doing composites in 112 and 113. In 112, we were doing composites here, and when we were doing inverse functions there, which we're doing this morning, we're doing inverse functions here. So they're sort of mapping each other fairly nicely here. But we're still in Chapter 4, Trigonometry, now in 4.7, Inverse Trigonometric Functions. Okay. Where we're going to go here, our objectives are to evaluate and graph, this book loves graphing, the inverse sine function. We'll evaluate and graph the other inverse trigonometric functions, or at least some of them, and we'll evaluate the compositions of trigonometric functions, which is something else we did in 112 yesterday, Tuesday and today. Okay? So the inverse sine function. Well, what can you remember about inverse functions? What has to be true about a function for it to have an inverse? Anything? Way back in pre-calculus algebra, I know it's a long time ago. What had to be true before it could even have an inverse? These are signs telling you whether to steal third or not. Okay? 1 to 1. Oh, yeah, they have to be 1 to 1. What in the world do we mean by a 1 to 1 function? Anyone recall? No. Okay. Does anyone recall what it means to be a function? Period. What visual test can we use on the graph of a function to tell whether it's a function or not?
It has to be a variable.
Say again?
Doesn't it have to be a variable?
It has to be a variable, yeah. Functions all have variables, right? But what visual test can we run to know whether a graph is a function or not? Say again? The vertical line test. Remember that? If you have a graph of a function, if a vertical line ever intersects a graph more than once, not a function. Because remember, to be a function, for any value of x, it can have one and only one y. Right? Okay, that's to be a function. To be a one-to-one function, not only does it have to pass the vertical line test, it also has to pass the horizontal line test. Meaning a function cannot back up on itself. Here's the other way to express that. To be a one-to-one function, you have to be strictly increasing or strictly decreasing. Otherwise, it'll fail the horizontal. If it backs up on itself anyway, then it's not going to be a one-to-one function. Okay? Now, let's think about sine functions. How do they look? Right? Are they going to be one-to-one? They're going to pass the horizontal line test everywhere? No! Okay? For instance, the x-axis of the horizontal line, it crosses many times. So what you have to do for an inverse sine function to have an inverse, you have to restrict yourself to a portion of the domain where it's either strictly increasing or strictly decreasing. Same true for every one of these functions. So, inverse sine functions are not going to be defined everywhere only for very specific domains of the sine function. Okay? So here's what we have. We know that for a function, to have an inverse function, it must be 1 to 1. And y'all remember that well, I recall. Right? Okay? It must pass the horizontal line test. Yeah, y'all got that right on. Okay? And from this figure, you see sine function. No way it's going to pass a horizontal line test. It's going to cross lots of these horizontal lines multiple times. Unless you restrict it to some specific domain here from, say, minus pi halves to pi halves, then it passes the horizontal line test there and there only. So sine x has an inverse function only on that interval. Can I have one here or here? Yeah, maybe here, but not here, you know. So usually we would use only that minus pi halves to pi halves. Okay? And I think that just about ran us out of time, didn't it? Okay. Well, let's see. All right. There are a few other things. Let's just do those next time. So we'll start with this however. So we didn't get very far here, but we did get a little ways. And we'll go from there. All right. Have a good weekend. We'll see you on Tuesday.
You said you didn't get any reading papers from this class?
I'm sorry?
You said you didn't get any reading papers from this class?
Any research papers?
Yeah.
Oh, you emailed one, didn't you?
I gave it to you Tuesday.
You did. When was it? Recently?
This Tuesday, yeah.
Oh, yeah. I haven't gotten those graded yet. Sorry. Yeah. I meant, I was just looking in the book. Sorry. I haven't graded it yet, so I didn't see it here. Yeah. Thank you for reminding me.